It's my great pleasure to introduce our Dean Distinguished Speaker today, Professor Kirk Schanze, who received his bachelor degree in chemistry from Florida State University in 1979, and his PhD in chemistry from the University of North Carolina in 1983. He was appointed Miller as a Miller postdoc fellow at the University of California, Berkeley from 1984 to 1986. And then he started his independent faculty career at the University of Florida in 1986. Kirk was a university distinguished professor at the University of Florida until 2016. He is currently the Robert Walsh Distinguished University Professor at the University of Texas at San Antonio. He was a senior editor of ACS journal Langmuir from 2000 to 2008, and then from 2008 to 2023, Kirk was the editor-in-chief of ACS Applied Materials and Interfaces and the ACS Applied Material Journal, a family journal, which is 7 journals. He is currently serving as deputy editor of ACS Central Science, which is a flagship diamond open or free open access journal published by ACS. He is authored and co-authored for more than 380 papers, articles on basic and applied research, with a primary focus on organic and organometallic material chemistry, and he's inventor and co-inventor for more than 20 different patents. So welcome, Professor Kirk, and now the mic is yours. Thank you.
Thank you, Omar, and thanks to everybody for coming this afternoon, and thanks to very much for the kind invitation to come back to KAUST. I've been here a few times before, but it's been about 9 years, I think, since the last time. So I can see definitely changes in Saudi Arabia as well as changes here at KAUST. And I look forward to meeting more of you this afternoon, and as the week progresses. I'll be here all week. So anyway, so I'm going to talk about some work that my group has done for quite some time, going back about 20 years. And I'll start out a little bit with the history and background of the area, but the theme is a family of materials that we call conjugated polyelectrolytes. So these are conjugated polymers that bring together the optical and electronic properties of conjugated polymers with water solubility imparted by ionic character. And so I don't think probably most of you in the audience don't need an introduction to conjugated polymers, but as you know pretty well, these materials are based on organic chemistry. They have the advantage that we can use organic synthesis to guide the structure and control the properties, optoelectronic, meaning both the optical and the electronic properties. And there's a variety of applications, most notably light emission and electronic properties, as well as applications in solar cells. So what I'm going to talk about today is a special class of conjugated polymers. So it's a subset of the broad class of conjugated polymers. And we call these materials conjugated polyelectrolytes. Bear with me for a minute as I get used to this funky pointer. So what a conjugated polyelectrolyte is a polymer that brings together the character of a conjugated backbone. So for example, the well-known polymer polythiophene, polyphenylene, vinylene. I'm going to talk a lot about this family of polymers that we call polyphenylene ethynylene. So the backbone is likely familiar to you if you're familiar with conjugated polymers. But what's unusual about these materials is that they have charge groups on them. And that makes these materials belong to the family of polymers that we call polyelectrolytes. So they're polymers with permanent ionic charges. The most notable aspect of these materials is that they're water soluble, so we can dissolve them in water and process them from water. But probably what's a little more subtle and something that we've learned over the years and that I'll teach you about today is the fact that when you have a polyelectrolyte, such as shown here, a chain that has permanent charges, that brings along an environment of oppositely charged ions. And it turns out the interaction between the polyion and these oppositely charged ions can be quite profound in solution as well as in the solid state. And it can give rise to very interesting and useful properties. And I'll talk some about that today, both how the properties can modulate, these interactions can modulate the properties of the polymers, but also taking advantage of them to use them in sensing applications. So I think it's kind of nice for a general audience to give you a little bit of history. So I'll tell you a little bit about where this field comes from. And not surprisingly, it starts with one of the pioneers in organic polymers, and that's Fred Woodall. Fred's group was working on conjugated polymer synthesis in the early days in the 1980s and 90s. And not surprisingly, his lab was the source of the first conjugated polyelectrolytes, that is, conjugated polymers with charged groups. There's a paper that appeared in JACS in 1987, and it's a short paper, and it reported the synthesis of this polythiophene with negatively charged groups on it, and it's really just a synthetic paper. But if you read it really carefully, they talk about the fact that the polymer was water soluble, and it showed the color characteristic of polythiophene, an orange-yellowish color, and it was faintly luminescent. That's basically what they say in the last couple of paragraphs of the paper. A couple of years later, Woodall and his coworker Shi reported this polymer that's called MPS-PPV. It's a polyphenylene vinylene polymer that contains sulfonate side groups. And interestingly, if you look really carefully, this is the first soluble PPV derivative that was reported. It comes out before MEH-PPV. And I asked Fred about it when we were meeting a couple years ago, and it turns out they were patenting the MEH-PPV synthesis, and so they reported this in place of that. But it turns out this polymer is pretty interesting in its properties and applications, and I'll show you why. But again, this paper also is really just a synthetic paper. It doesn't talk much about the applications or potential applications. So about the same time, Tim Slauger's group was working on conjugated polymers, and Tim was pretty interested in sensing. And a paper that came out from his lab in 1995, it's in JACS, and it's not on conjugated polyelectrolytes, but you'll see in a moment why it's significant. What they did is they showed that if you made a polymer, this is a PPE type polymer that has a receptor group that can bind to a electron acceptor called methylbiologen. They showed that the interaction between the polymer and that quencher, that's a quencher for fluorescence, gave rise to what they called amplified quenching. And basically the idea is that if they compared the efficiency by which the biologen quenched a monomer compared to a polymer, the polymer was quenched in the range of 100 times more sensitively for the same amount of biologen added. And they coined this amplified quenching, and this paper that came out in 95 had no application. It was just a fundamental study, but it gave rise to this concept of the idea of getting enhanced sensitivity and quenching if you used a polymer combined with a fluorescence quencher. Okay, so now I'm going to come back to the story of conjugated polyelectrolytes. So this is where these two ideas come together. It turns out the way this happened is my friend David Witten, turns out he was my PhD advisor, but we have collaborated throughout most of our lifetime since I was quite young. And Dave came together with Duncan McBranch at Los Alamos National Labs, and McBranch was a student from Woodall's group, Woodall and Heeger together. And so McBranch brought with him this MEH-PPV derivative that we saw a moment ago that Fred's group had synthesized. And what Dave brought was insight into fluorescence quenching of charge quenchers like methyl bioagent, and he had spent a lot of his lifetime studying quenching in mice cells, which are kind of like polyelectrolytes. And so these two guys got together and they decided, well, what happens if we take Fred's polyanion and we look at the quenching with methyl bioagent? And it turns out what they found was that they saw the swagger effect. They saw what is called amplified quenching. And I'm going to tell you more about the idea, but for those of you who know something about quenching already, they found that the Stern-Volmer constant was about 10 to the 7th per molar. And what that means is that if you just add in the range of 10 or 20 nanomolar of this quencher ion, you can basically turn off the fluorescence of the whole polymer. And so this pretty interesting effect, it brings together Swagger's amplified quenching with the polyelectrolytes. So this paper went a little bit further, and they showed how you could bring together this sensitivity that's imparted by the polymer and this quenching phenomenon and use it in a biosensor. And what they did was a very simple scheme, is that they covalently linked the quencher, which is a bioagent, to a biorecognition element, which is biotin. And when they add this conjugate to the polymer's fluorescence is quenched. And it takes just a very small amount because of Swagger's amplified quenching concept. But then if you add the protein, which is the partner for biotin, that protein is avidin, what happens is that the biotin-avidin interaction takes over and it basically moves the quencher away from the polymer and the polymer's fluorescence turns on. And so now what you've done is you've made the polyelectrolyte basically a transducer, and the signal that it transduces is the binding event between the protein and the biotin. So you can basically use the polyelectrolyte as a transducer in a signaling event. So this paper, which was published in 1999, basically got this field going, and at this point now, this is about a year or two ago, it's gotten over 850 citations, so you can see it kind of blossomed into a sub area of conjugated polymers. So in the preceding few years, several other groups got involved. My group became interested through our interactions with David Witten. We reported the first synthesis of this sulfonated polyphenylene ethynylene compound. That was done by Chunyan Tan, who was a graduate student at the time, and Mauricio Pinto, a postdoc. And at about the same time in 2002, Guy Bazan and Alan Heeger together reported the properties of this cationic polyphorine derivative. And as you'll see, Bazan and Heeger began to do sensing work. They developed ways of using that cationic polyphorine as a sensor for DNA hybridization. And they started publishing papers in that area starting in the year 2002. And as you'll see, my group became interested also in sensing application, and I'll tell you more about that story going along. So where the field is at now, it's developed, and I'll show you some of the things that we've done over the years. More recently, the work that's going on in the area is mostly focused on biological interactions, and I'll tell you about some of our work in that area going forward. Of course, we're taking advantage of the water solubility of these interesting conjugated polymers and their interactions with cells and microbes, as well as ion sensing, and I'll tell you a good bit about the story that we've worked on with respect to sensing phosphate ions and coupling that with enzymes using positively charged conjugated polyelectrolytes. Okay, so I'm going to start kind of at the beginning in my own group story. And this has started out with just fundamental work where we were beginning to explore the properties of these water-soluble conjugated polymers. And as I mentioned before, we had synthesized this sulfonated polyphenylene ethynylene. The molecular weight of these materials typically is around 20 to 50,000 Daltons. That corresponds to in the range of maybe 100 to 200 repeating units. So they're moderately sized molecular weight polymers. And as I mentioned before, they're quite soluble in water, but they're also soluble in polar organic solvents like alcohols. And Chunyan Tan was studying this polyelectrolyte just in terms of its fluorescence properties, and she found quite an interesting effect that at first we were a bit confused by. And the easiest way to think about it is just to look at the color of the fluorescence by eye. In an alcohol solution, the polymer is a blue fluorescent, and it appears as this structured emission band. And for those of you who know something again about conjugated polymer photophysics, you would recognize that as being a typical fluorescence for a conjugated polymer, meaning that the Stokes shift relative to the absorption, which is in blue, is pretty small. So it looks like what you would expect for this family of polymers. By contrast, in water, the fluorescence is weird. It's green in color by eye, and if you measure the spectrum, it's this broad sort of emission that peaks at about 550 in the green region of the spectrum. And at first we were confused. I told Chunan, go back, try again. There's something wrong with your solvent. I don't understand what's going on. It turns out this is very repeatable. There is clearly some effect that's taking place. And after doing quite a bit of work over several years, we've come with a model which basically understands the idea that these polyelectrolytes are actually existing as mostly unaggregated individual chains in low molecular weight organic polar solvents like alcohols. But in water, these materials aggregate, and they form structures that we believe have some organization. But in particular, because of the aggregate structure, there's close contacts between the polymer chains and the aryline units, and those give rise to what we call an excimer-like excited state, meaning that when you excite the material, the excitation is delocalized over more than a single chain, and that gives rise to this very profound shift in the emission spectrum and the broadness of that emission. So this was a fundamental effect. I should mention that we have quite a bit of evidence for the existence of these aggregate structures using light scattering methods as well as fluorescent scattering methods. And in addition, it's very likely that this aggregation is driven by a hydrophobic effect. It's much like the formation of soap micelles that occurs when you put soap molecules into water. So that's a fundamentally interesting effect, but now I'm going to tell you a little bit about how you can harness this to do something useful. And this work was done sometime later in the year about 2010, and a student that was working in my group at the time, his name was Xiaoyong Zhao, he was synthesizing positively charged conjugated polyelectrolytes. And in particular, he had made this polyelectrolyte that has these ammonium groups with these branch side chains. And the goal that we set out when we designed this polymer was to make a polymer that would be very water soluble, taking advantage of the high charge, but also using these branch groups to keep the polymers apart so they didn't aggregate. And it turns out we were successful. This polyelectrolyte in water exhibits the blue fluorescence that's characteristic of the unaggregated polymer. But what we found out quite interestingly is if you add this ion to the solution of that polymer in water, this ion is called pyrophosphate by the biologist, or sometimes it's abbreviated PPI. It turns out PPI induces the polymer's fluorescence to go from that blue to green color, characteristic of the aggregation. And we think that what's happening is that the pyrophosphate essentially has a molecular recognition and ionic interaction with these positively charged ammoniums, and it bridges at least two chains, which then collapse into an aggregate structure. It turns out, as I'm going to show you, the aggregation is also reversible. So if you remove pyrophosphate from the solution, you can recover the molecularly dissolved polyelectrolyte. It turns out this effect takes place at relatively low pyrophosphate concentration. And so, as shown here, it can be a useful sensor for just the presence of pyrophosphate in a solution. But as I'm going to show you a little bit later, we can also couple this with enzymes and use it as an enzyme biosensor. Okay, so before I go any further, I want to come back and talk about this effect that I called amplified quenching that came from that original Swagger paper. But in order to talk about that somewhat quantitatively, I need to teach you a little bit. Most people are not familiar with fluorescence quenching, so I'm going to give you a kind of a lesson on fluorescence quenching. The basic idea is that if you have a fluorescent material, it can be a molecule, it can be a polymer, or it can be a nanomaterial. In any case, if you add to it a second species, we'll call that Q for quencher. What can happen is that as you add more amounts of the quencher, the fluorescence gets weaker. That's the effect we call fluorescence quenching. And we use the I0 to represent the intensity before you add any quencher, and then as you add more quencher to it, we represent the intensity by the symbol I. There's a famous analysis of this type of experiment, and it's called the Stern-Volmer analysis or the Stern-Volmer equation. And the equation is written here, but mainly what I'm going to have you look at is that the Y component is that fluorescence intensity divided by the quenched intensity, so it's called I0 over I. And we make a plot of that inverse intensity versus the amount of quencher added. And the reason we plot it this way is that Stern-Volmer predicts that this should be a straight line. And the slope of the line is called the quenching constant, KSV. Okay? And in most simple systems, molecular systems where you add a molecule as a quencher, you get a nice straight line. And typically, if it's a small molecule and it's a fluorescent molecule with a lifetime in the range of a few nanoseconds, it turns out you'll get a typical slope of in the range of around 10 per molar. Okay, now that probably doesn't mean much to you right now, but just pay attention to the units. That's inverse molar, so this is 1 over concentration. Okay, and what does that Stern-Volmer constant really mean? Well, what it means is that if we take the inverse of that number, 1 over 10, that corresponds to the amount of quencher that you need to add to get 50% quenching. Okay, so in other words, it's how much I need to add to drop this intensity down to half of what it started at. So now if we think about a sensor, a 50% reduction in intensity would be a pretty good response. So that would be a reasonable fluorescence response to the presence of an analyte. But if you're an analytical chemist, you're going to conclude that this is a pretty poor sensor because you're going to have to add 0.1 mole per liter to get a 50% signal. Okay, so this is a bad sensor, but it gives you the idea. Okay, so now let me come back to the story of amplified quenching, and I'm going to tell you about how it works with these polyelectrolytes. So I'll start here with this idea. If you take this simple molecule that's called stilbene, it's a molecular fluorophore, and you add viologen to it as a quencher, you'll get that 10 per molar slope that I told you about. So not a good sensor. If you take this molecule, this is a charged molecule, but it's still a molecule, and you quench it with viologen, now you get a slope of 10 to the third. That's 1,000, okay? So you get a big amplification. Why is that? It has to do with the fact that you get ion pairs formed. So the two species come together, and that gives rise to what we call static quenching. So the preformed complex is just immediately quenched, and it enhances the quenching. But that's still not a very useful sensor because that means that you could measure this concentration in the millimolar range. So it's a fair sensor, but not a really good one. If you take the same fluorophore and now you put it into a polymer, now what you see, interestingly, is you see this amplified quenching effect turn on, and the Stern-Volmer goes to 1,000,000. So now you've got a real kick in amplification, and that means that you can measure the concentration of this down in the low micromolar range if you were thinking about sensing. And it turns out under certain conditions where these polyelectrolytes are aggregated, which is pretty common, you can see these Stern-Volmers go into the range of 10 to the 7th to 10 to the 8th. So you can get really, really high quenching constants. And that now means that in terms of sensing, you can detect things like this viologen in the low nanomolar range. And just to give you an idea, visually what this means, this is our polyphenylene ethynylene sulfonate. These are actual photographs of solutions of that polyelectrolyte with 0, 50 nanomolar, and 100 nanomolar viologen. And you can see quite visible quenching, which is very easily detectable by using spectrophotometers. So this is the idea of amplified quenching. it allows you to measure these effects at really low concentration. So now, one of the things that my group has been interested in over the years is what is the mechanism of this effect? And I'm not going to give you a long story about that, but I'll just tell you that it really has two components. The main component is this static quenching, meaning that the opposite charges bring together the quenchers and the polyelectrolytes. That enhances the probability of the exciton being in close proximity to the electron acceptor or the energy acceptor. But then there's also an effect that has to do with diffusion of the excitons along the polymer backbone. And this is actually what, if you read the original Swagger paper, he really sort of emphasizes this effect. But it turns out, in my estimation, the exciton diffusion is not as major a role as really just the static quenching part, that is, the two species coming together and being in relatively close proximity. Okay, so now I'm going to come back to the application of using this effect in sensors. And some of the first work that we did, it goes back now about 20 years. We published this paper in 2004. And what we were interested in doing was trying to bring this amplified quenching idea together with the polyelectrolytes to do biosensing. And the scheme that we came up was pretty simple. The idea was that we developed a quencher ligand, where the ligand is a substrate for some protein that can act as an enzyme. The ligand has a positive charge that delivers the quencher to the polyelectrolyte. And so in this form, the system is off. There's no fluorescence. And then when you add the target, in this case, it's a proteolytic enzyme, that enzyme cleaves a bond, releases the quencher, and the fluorescence of the system turns on. The idea, again, remember, is because of the amplified quenching effect, you don't need to add very much of this quencher to the polyelectrolyte to essentially turn the system off. And that also means that you don't need much of the enzyme to recover the fluorescence. So it's an enhanced signaling system where the polymer is just acting as a transducer. It's measuring the presence of the quencher in the system. So we developed that, and one of the things that we did was look at the detection limit of this system. The one that I'm showing here is where we used a tripeptide. It was labeled with a para-nitroanilide as a quencher group, so para-nitrobenzene is a good electron acceptor. So that's taking the place of what I've used bioagent for previously. And when you add this tripeptide with the para-nitroaniline on it to the polyelectrolyte, you turn off the fluorescence. In this case, we bring it down about 75%. And in this case, we've added this should be micromolar, not millimolar, so it's 1 micromolar of the tripeptide. And then we add the enzyme, and the enzyme that we used was thrombin in this experiment. And over a period of about 1 hour, you can see the fluorescent signal recovers, and that's due to this slow hydrolytic reaction that's causing the para-nitroanilide to be released from the tripeptide. And doing experiments where we measured the detection limit, it turns out we were able to measure the enzyme down at about 50 picomolar concentration, again, using about a 1 hour incubation time. So we basically mix the system together and then read out the fluorescence after an hour of incubation. So moving on, we were also interested in looking at ion sensing. And I come back to this student. His name was Xiaoyang Zhao. He was a really productive student at the University of Florida back during the time that this work was published in 2007 or so. And Xiaoyang had been making these carboxylated polyphenylene ethynylenes, again, a family of water-soluble, negatively charged polyelectrolytes. And the story that Xiaoyang tells, this is really his own work and design, was that he had made these polymers, actually made a family of them at different molecular weights, but he had submitted an abstract to an ACS meeting where he was reporting that he was going to talk about ion quenching of the fluorescence of this polymer. And so he came in one weekend and took this polymer, and he did quenching experiments with a variety of different metal ions. And by quenching, what I mean is he added different amounts, did the Stern-Volmer experiments. And what I'm showing here is basically a summary of the result, and that is, this is a fluorescence of a series of vials of the polymer, and it's green fluorescent. And what you can see is when you add 10 micromolar of all these different metal ions, Most of the vials are still fluorescent, but the one that has copper-2 is dark. And so that means that copper-2 is the most effective at turning off the fluorescence of this polyelectrolyte. If you measure the Stern-Volmer slopes, they're shown here. So these are the Stern-Volmers. That's copper. The Stern-Volmer is around 2 times 10 to the 6th, so it's a pretty efficient quencher. It turns out all the others are actually still give some quenching, but compared to copper, they're much less efficient. So the question that we ask first is, why is copper so efficient? Does anybody have any ideas? Why does copper work better than, say, cobalt or nickel, which you might expect to be good fluorescence quenchers, by the way? All these metal ions can quench. So what's special about copper? Anybody have an idea? Carboxylate? No, it actually has to do with just binding to carboxylate. It is acting as a redox quencher. It's an electron acceptor, but it turns out nickel or cobalt can also be electron acceptor quenchers. But if you look up in a table of inorganic chemistry stability constants, divalent copper among all these metal ions has the most stable binding to carboxylate. So it's really the effectiveness at which the carboxyl brings the ion to the polymer backbone, and that's what dominates. So it's this static quenching idea that's enhanced again because the polyelectrolyte is very efficiently quenched once the quencher is nearby it. So that's quite interesting, but it gives us some insight into what's driving this effect, and that is the binding of the metal to the carboxylate. And so what Xiaoyang did next is that he said, okay, well, if it matters what is binding to the polymer backbone, what if I disrupt that interaction? And so what he did is he took that system, which I just mentioned, polyelectrolyte, you add divalent copper to it, and this is a cartoon representing that state. The polymer is aggregated and it's got copper ions on it, and it's not fluorescent. But then what he showed is that if you add pyrophosphate, this negatively charged phosphate ion, you can quantitatively recover the fluorescence of the polyelectrolyte. And what's happening in this case is that copper is being sequestered by the pyrophosphate. The pyrophosphate is acting like EDTA. It's sequestering the metal ions, and it takes them away from the polymer, and that causes the fluorescence to recover. So it's basically reversing that binding effect that I mentioned previously. And this is a titration experiment where now we're just measuring the fluorescence intensity as we add pyrophosphate, and you can see that it recovers, and it actually almost recovers 100% of the initial intensity before the copper was added. And it turns out it's rather selective. This is a bunch of different anions that were compared, and you can't see the vials because they're all quenched. They have copper in them. The only one that's unquenched or turned on is the one that has pyrophosphate in it. So it's a reasonably selective and quite sensitive sensor for pyrophosphate. Okay, so going further now, so I'm going to show you how now you can take a step beyond this and use these kind of systems as biosensors. The basic idea is the following. This work was done by Nancy Liu, who was a concurrent graduate student with Xiaoyang in my group at the time, and Nancy was an analytical chemist. And what we knew at the time was that pyrophosphate, this diphosphate, can act as a substrate for an enzyme called alkaline phosphatase, sometimes abbreviated ALP. And what ALP does is it catalyzes the breaking of this POP bond, breaking down pyrophosphate to monophosphate. So in this case, what you do is you take the polymer, it's fluorescent, you add copper to it, it's turned off, then you add pyrophosphate and it's turned on. But in this system, you have the three components present. You've got the copper that's sequestered with the pyrophosphate, and you've got the polyelectrolyte, which is fluorescent. But now if you add the enzyme to it, the enzyme begins to catalyze the hydrolysis, and the copper goes back to the polymer, and the fluorescence turns off. And you can see that experiment here in real time. This is representing the fluorescence of the polymer in the green region, and these are different amounts of the alkaline phosphatase added, 5, 10, 20, 50 nanomolars, and so on. And you can see over time of about 10 minutes, the fluorescence is going down. And that decrease in fluorescence is due to the recovery of the fluorescence of the polymer due to the copper going back onto it. And basically it's transducing the hydrolysis reaction of the pyrophosphate by alkaline phosphatase enzyme. We actually were able to calibrate these enzyme kinetics with known kinetics of the enzyme under the same conditions. And so now what we're using is this nice fluorescent conjugated polymer as a sensor for a bioreaction. Nancy, as part of her thesis, sort of generalized this to a family of different enzymes that basically take advantage of the same kind of catalytic effects, but using the polymer again as a transducer. Okay, so I showed you this slide before, and I want to show you now how we can make the sensor a little bit more simple. And what I showed you before is this more complicated positively charged polyelectrolyte. And I told you that if you add pyrophosphate to that polymer, you can directly induce aggregation. And now you know from what I told you previously that if we add alkaline phosphatase to a solution of pyrophosphate, it's going to break the pyrophosphate down into monophosphate. So if this reaction that I'm showing here, that is the aggregation, can be reversed, we can take advantage of the reversal of the aggregation to measure the hydrolysis of PPI by an enzyme. And so that's what I'm showing you here. So now the system is simpler. We don't have copper. We don't need the divalent metal ion present. We just basically start out with the fluorescent polymer. We add the phosphate to it. It aggregates. And then we add the enzyme. And the enzyme catalyzes the hydrolysis reaction that's shown here. And during the hydrolysis reaction, the polymer is deaggregated and it becomes blue fluorescent again. And in this case now we have a fluorescence turn on, so the fluorescence is going up with time. And you can see it has similar sensitivity to the one that I showed you before, but because it's simpler, we don't need to add the metal ion to it. It turns out there's some complexities with these enzymes. It turns out, for those of you who might know something about kinase enzymes like ALP, they always require the presence of a divalent metal like zinc or magnesium present in the solution, and that can interfere with the copper that's added to that other enzyme system. So this system that's metal-free essentially freezes from that limitation, and it's much more generalizable. Okay, so that's all I'm going to say today, I think, about sensing. I'm going to now turn and talk about some other effects. Actually, I'm going to talk a little bit more about sensing, but the rest of the talk, I'm going to focus more on positively charged polyelectrolytes, and this is more what we've been working at in the past 5 to 10 years. I've already told you a lot about this polyelectrolyte and its ion sensing properties. We've explored these imidazolium polymers. More recently, we made these phosphonium polyelectrolytes, and I'll tell you a little bit about a polythiophene that also has an imidazolium group on it. So we've been kind of exploring the space of different charge groups, again, looking at these positively charged ions as adjuvants to the polymer backbones. So I misspoke. I'm going to come back to sensing for just a couple of minutes. And what I want to do is come back and talk a little bit more about how this polyelectrolyte, this positively charged guy, interacts with different phosphate ions. And as you know, I've talked about pyrophosphate. That's diphosphate. There's many polyphosphates that are present in nature, and some well-known ones are the nucleotide phosphates, such as ATP, ADP, and AMP, and those different terms represent the number of phosphates that are connected to the sugar part of the nucleotide. And what we've done is looked at how these different phosphates interact with these cationic polyelectrolytes, and in particular, what I'm showing here is this branch polyelectrolyte. And it turns out, not surprisingly, is that it interacts most strongly with the adenosine triphosphate. It takes only about 10 micromolar to induce very significant quenching of the fluorescence. The diphosphate analog, ADP, we have to add more of it, and it doesn't quench quite as efficiently. By contrast, the monophosphate, or just monophosphate alone, really doesn't give any quenching at all. So it takes at least 2 phosphates, and 3 is better than 2. But what's a little bit more subtle here is that if you look really carefully at these spectra, you'll notice that this isn't just simply quenching taking place. There's actually shifting going on in the spectra as you add more of the pyrophosphate, or in this case, ATP to the system. So we believe that there's some specific molecular interactions taking place that give rise to changes in the conformation of the backbone that are reflected in the emission spectra as you add more and more of the quencher. And what I'm talking about here in particular is you'll see this peak that starts out at about 420 nanometers. It shifts to about 430 or so as you add more of this ATP, and then finally it basically quenches almost all of it and becomes this broad-shaped spectrum. This is a cartoon. It's not supported by any real data, but we think that there are specific interactions that are taking place at the molecular level that have an effect on the conformation of the backbone, and that's possibly what gives rise to these shifts in the spectra. But what's useful in this case is that there is a shift, and it's reproducible, and it depends on which phosphate that we use. And so that's a basis for using machine learning or training to basically build a sensor. And I had a student who was quite interested in AI, and this actually goes back to before the AI boom. This work was done in around 2017 to 2018, and we published it in 2019. But what my student Yun Huang did was he took that polyelectrolyte and he looked at the quenching of it with a variety of different phosphate derivatives, ATP, GMP, et cetera, and then also using some oligonucleotides. And then he trained essentially the spectra with different machine learning models. And he was able essentially to discriminate based on the spectral shape which polyelectrolyte or which ion the polyelectrolyte was interacting with. So he could identify the nature of the phosphate in the solution just based on a training model. And again, what that's based on, as I mentioned, is the change in the shape of the emission spectrum as you add the phosphate to the solution. So it's basically not a sensor concentration, but rather it's a sensor identification technique. So more recently, as I mentioned, one of my students has been looking at phosphate or phosphonate derivatives. Again, the polyphenylene, ethynylene backbone, but now we're using these positively charged phosphate side groups or phosphonates. And he made a family of these. And as part of his work, he was also looking at what happens when you add different phosphates to this polyelectrolyte, and you see similar effects. You get aggregation induced by the interaction of the polyelectrolyte with the phosphate. But the reason I'm showing you this is that there was something that popped out of this just by accident that's kind of interesting, and we don't completely understand what's going on. But if you look at the spectra, and it's one particular member of that family, it's the structure shown here where the side chain has 3 carbons in it, and every phenylene repeating unit has positively charged groups on it. When you add ATP to that polyelectrolyte, you see some really interesting shifts in the absorption and interesting shifts in the emission. And in particular, it's this feature that we see in the absorption. For those of you, again, who might be familiar with photophysics, it looks very much like the signature of what's called a J aggregate. And a J aggregate is where chromophores align in a long axis form. So like if you think of the polymer chains, somehow they're aligning in such a way that the chromophores are lined up and you get the transition dipoles so that they couple, and it gives this what's called superradiance effect where you get a very sharp and narrow absorption feature, and you also see a sharp emission feature that corresponds to that. This cartoon represents what we think that structure might look like. It's some sort of aggregate that has alignment of polyelectrolyte chains such that the dipoles that are oriented along the long axis can couple, and it's that coupling of the transition dipoles that gives rise to these very sharp absorption peaks. Quite interestingly, if you look carefully at the solutions using microscopy, we can see that there's formation of aggregate structures that have sort of kind of like capsule-like shapes, but they're not all closed. They tend to have a broken capsule shape like is shown here. You can see the scale bar is 5 microns, so these capsules range from a few 100 nanometers up to a few microns in size. So there's clearly the templating of a unique aggregate structure that has molecular order as well as long-range order that gives rise to these capsule-like shapes. Okay, so that's the end of that part. And finally, I'm just going to talk about one other application. And to sort of bring that story some background, I'm sure everybody's familiar with the idea of antibiotics. These are chemical substances, drugs that act to kill bacteria quite effectively. There's many types of antibiotics. There's classical drug antibiotics. There's things like silver. Colloidal silver is quite effective. But it turns out there's still the need for other kinds of antibiotic agents, that is, materials that can actively and effectively kill bacteria. And part of the background for that is the reason that there's a rise in what are called traditional antibiotic-resistant bacteria, or MRSA. These are bacteria that really resist traditional antibiotics. So I'm going to talk about a mechanism that involves light. So these polyelectrolytes absorb light, and that creates excited states. I've been talking about fluorescence from an excited state. It turns out there's another type of excited state that can be produced on excitation of these materials, and that's a triplet excited state. And triplet excited states are well known to interact with oxygen in different ways to generate either radical type species through what's called a type 1 sensitization mechanism, or generate reactive form of oxygen called singlet oxygen, and that's called a type 2 photosensitization mechanism. Both of these forms of reactive oxygen, radical oxygen or singlet oxygen, are really toxic to microbes and mammalian cells, and so they're quite effective at essentially cytotoxicity. Okay, so what about these polyelectrolytes? Well, it turns out they're pretty effective, we know, at generating singlet oxygen, which, as I mentioned, is a reactive form of oxygen. We can measure that in several ways. This is a polyphenylene ethynylene. That's, in this case, it's dissolved in methanol. And when we irradiate the polyelectrolyte, we create an excited singlet. It undergoes intersystem crossing to a triplet. And that triplet then can react with ground state oxygen to produce singlet oxygen. And we can detect that by the emission that occurs in the near infrared. And so we can measure the oxygen that's produced, the singlet oxygen, and quantify it with a quantum yield. This polyelectrolyte, under the conditions that I talk about here, generates singlet oxygen at around a quantum yield of about 13%. So it's a moderately efficient singlet oxygen generator. So that's the first part of the story. The second part is what happens if you mix these polyelectrolytes with a suspension of bacteria. It turns out they very effectively and very rapidly coat the bacteria. This is some recent work done by Isai, one of my graduate students who just finished his PhD, and he was the one who had made these positively charged phosphonium polymers. It turns out when you mix these polyelectrolytes with Staph aureus in solution, very rapidly the bacteria glow a green-yellow color. That's the characteristic fluorescence of the polymer. If you look very closely, Staph aureus are like little spheres, and it turns out that the green fluorescent polymer is coated on the surface of the bacteria, and you can see that from line scans. If you do a scan through the bacteria, you see the fluorescence peaks around the periphery, so it's coating the surface of the bacteria. Okay, so the next idea is what happens if you take those coated bacteria and you expose them to light. This was first discovered about 20 years ago by Dave Witten. I've mentioned his name a few times, and he and I have collaborated together in this area for quite a long time. But it turns out if you take those polymer-coated bacteria and you expose them to light for a relatively short period of time, the bacteria are inactivated. The experiment I'm showing here is called a live dead assay, and it turns out, simple way to think about it is that the green bacteria in this image are alive, their membranes are intact. After exposure, the dead bacteria membranes are compromised, glow red, and that's because you add a second dye. So it's a way of measuring the cell death that's induced by irradiation. So Dave first reported this effect back in 2005, and together he and I have been working on this area for quite some time, and I'll show you some of the different results. This basically highlights the mechanism that we think is going on, is you've got a positively charged polyelectrolyte, it interacts pretty strongly with the phospholipid membrane on the surface of the bacteria, and that brings the polyelectrolyte into close proximity. Light exposure generates reactive oxygen species, which then react with cellular components and inactivate the microbes pretty rapidly. So I'm coming back to polythiophene. For those of you in the field of conjugated polymers, polythiophene is probably the first polymer that you ever thought of. This is a polythiophene that's got a positively charged imidazolium group on it. And believe it or not, this polymer is the most effective antibacterial polymer that we've discovered to date. And we think it has to do with two things. One, this polyelectrolyte is very hydrophobic, so it really interacts quite strongly with the membrane of the bacteria. But in addition, polythiophene has a pretty high triplet yield, so it's quite effective at generating reactive oxygen species, which we believe are the cytotoxic element that's produced on light exposure. So this polyelectrolyte, we've studied it with a variety of bacteria, but I'm showing here a comparison of the interaction with Staph aureus, which is an example of what's called a gram-positive bacteria, and E. coli, which is an example of what's called a gram-negative bacteria. In general, gram-negative is harder to kill than gram-positive. It has to do with the stability of the membrane. And what I'm showing here is different concentrations of the polyelectrolyte, 1 microgram and 10 micrograms up here, and red means light exposed, and green means no light. And you can see that at about 1 microgram per milliliter, we're getting up to close to 99.9% killing effectiveness. That's kind of the gold standard for bacteria. It's called 3 log kills. So if you get 99.9, you're doing pretty well. So this polymer, again, at 1 microgram with 1 hour of light exposure is getting almost 3 logs of kill of bacteria. Just to give you a calibration, a common antibiotic like ampicillin, to get this kind of killing effectiveness in an hour, you'd have to be at about 100 micrograms per milliliter. So this polymer is, in weight amount, is essentially 100 times more effective, but of course you have to add light as well to activate it. I mentioned also about a size work with these phosphonium polyelectrolytes. These are also pretty effective at killing. In the case of these guys, this work is done at 20 micromolar concentration, so it's higher than the polythiophene, but now we're up to almost 6 log kills. And what I'm showing here is a classic biological experiment where we're actually plating out the bacteria, and you can see this polymer, these are 6 log dilutions. You can see no growth of bacteria. So it's basically just wiping out the bacteria completely at 20 microgram per milliliter, and this is about a 20-minute light exposure in this experiment. Okay, so finally I'm going to close on a little bit of work that we've recently done on mammalian cells, and we have been working on this area. As background, we're working on a different class of materials. We call these conjugated oligoelectrolytes. So these are not polymers, they're small molecules, but you'll recognize the structures are similar to the polymers that I've been talking about. And again, working together with David Witten, we reported studies on these oligomers killing bacteria back about 10 years ago. Guy Bazan and his group kind of picked up on our work. They made these somewhat more elaborate structures that have these multiple charge groups, and they propose that they can span membranes like shown in this cartoon here. And so we became interested in this idea, but bringing it together with the donor-acceptor-donor type of structures that are used in polymers that are used in optoelectronic applications. So this graduate student, Kanya Jaina, made this molecule. It's a polyelectrolyte that contains this thiophene benzodiathiazole donor-acceptor-donor structure with these 6 positively charged groups on it, making it very membrane active. If you add this polymer to mammalian cells, the mammalian cells very rapidly take it up. These are images taken of a breast cancer cell line called HCC 1937. Most of the molecule is in lysosomes, but you can see a green sort of stripe around in this region. I'm trying to point at it. That's the nuclear membrane. So quite clearly the dye does go into the membrane. The different colors represent different lifetimes, by the way. This is a lifetime image. And it turns out green is a little bit of a shorter lifetime than the orange and yellow that we see when the molecule is in the lysosomes. But quite interestingly, if you then take those cancer cells and you expose them to light, just 5 minutes of green light, we can see pretty substantial killing effect. We can reduce the efficacy of the cells by about 80% under the conditions of the experiment that's shown here. These are 3 different cancer cell lines. And so we can reproducibly show cytotoxicity to mammalian cells using this material. We don't exactly know the mechanism. It turns out this molecule is not a super efficient singlet oxygen generator. It's got a pretty low energy triplet state, but we do believe that it is generating some sort of reactive oxygen, either singlet oxygen or perhaps oxygen type radicals through a type 1 mechanism. But nonetheless, it is able to kill the cells with light exposure. So I think I'll stop there. I've told you a lot about this family of materials that we call conjugated polyelectrolytes. They have interesting fundamental properties, but also a variety of applications in ion sensing and in biology. I didn't say anything about electronic applications, but there have been applications in that area as well. I could give another talk in that area, but I won't do it today. I will bring up that there's a review article that I wrote about 1.5 years ago with some co-authors that's in an ACS AMI, and it kind of gives a short summary of some of the things that I've told you about today. So if you're interested, you might dig up that article and take a look at it as a starting point. John Reynolds and I also wrote a review article more than 10 years ago that's also kind of picks up some of the early work in this area. Okay, well, with that, I think I'll stop. The work that I told you about was done over a long period of time, so it involved a lot of my students. My collaborators, John Reynolds and I, kind of started together in this area back in the late 1990s. I mentioned Dave Witten. Over the years, he and I have collaborated for more than 40 years. And Xu Wang is a professor at the Institute of Chemistry in Beijing, and he and I have also collaborated for quite some time. And most of our recent work has been funded by the Welch Foundation, which is a really generous agency in the state of Texas. It funds research in the chemical sciences. It's why I'm there, and it's a pretty nice resource to have. So with that, I'll thank you. Hopefully we can have a little bit of time for question and answers, but thanks again to Omar and all of you for hosting me here at KAUST.
Thank you, Kirk, for the nice and informative presentation. We have time to get a couple of comments from the audience. Yep.
Thank you very much, Professor, for the very interesting presentation. I have a couple of questions. The first one is if we can have an idea of the degree of polymerization for your conjugated polyelectrolytes after the chemical synthesis. And the second one is if immobilization of substrates or surfaces for sensing applications have been explored by your team or are currently being explored. Thank you.
Very much. Yeah, so I didn't talk at all about synthesis, and I could spend half of the time talking about synthesis, obviously. The way that we most commonly make these polymers, well, there are 2 approaches. One is I call the direct approach, and that's where we take an ionic monomer, maybe consider a sulfonated monomer, and we polymerize it. Most often these are step growth polymerizations. We use metal catalyzed coupling chemistry like Suzuki or Sonogashira type reactions. When we do a direct polymerization, unfortunately, we don't have an easy way to get molecular weight. And the reason is that the polyelectrolytes don't sort of do typical GPC analysis. So we've kind of worked at that. But in parallel, we also do chemistry where we make a precursor. So we call it the precursor approach. And as an example, let's say we have a carboxyl group. We functionalize it as an ester with long chains. We polymerize that. We get an organic soluble ester polymer. We can measure its molecular weight. And typical molecular weights we get are ranging from around 10,000 to maybe 50,000. So they're kind of typical step growth sort of ranges. The dispersities are maybe 2 by GPC, which is again typical for a step growth polymerization. A polymer like the structures I showed If we have a molecular weight of 20,000, that corresponds to a DP of around 50. So it's 50 to 100 is kind of typical. Then with that precursor approach, we cleave the side groups. So if it's an ester, we might add base and hydrolyze to release the polyelectrolyte. In that case, then we don't remeasure the polymer molecular weight. We assume it's what it was before we hydrolyze the ester. Okay, so we've done a lot of work like that over the years. But again, the range is, it's like any polymerization. Sometimes you get 5,000, sometimes you get 100,000. It depends on how careful you are with the conditions. But again, it's kind of typical metal catalyzed step growth polymerizations. So that was your first question. The second question had to do with maybe surface modification, I think. And so it turns out we have done quite a lot of that. The first work that we did and we've done over the years is what's called layer by layer deposition. And what I mean by that is if you have a polyelectrolyte and you've got a surface, polyelectrolyte in solution, you dip the surface in, the polyelectrolyte adsorbs to the surface, monolayer coverage. Then if you take that surface out and you dip it into solution of an oppositely charged polyelectrolyte, you coat it again. Then you come back, you coat it again, you can go back and forth, and you can build up multi-layer structures like that, basically about one layer at a time. So you can make a 10-layer structure that's about 10 nanometers in thickness. If you're really patient and have a robot, you can make a 50-layer structure, which is about 50 nanometers. So we've done that kind of work. You can make sensors with them. It's probably not the best format for a sensor. Where we've used those more is in applications like thin film applications. We actually made some solar cells using that layer by layer approach. We've also made dye-sensitized solar cells where you take metal oxides and you surface modify them. So absolutely, you know, the films have interesting properties and can be useful. Thank you.
Yep.
You're up.
Thank you. Hi, thank you so much for your talk. I actually learned a lot today. I have a couple of questions regarding your first work. Mm-hmm. So I noticed that sometimes during the MEH PPV, you use either carboxylates or sulfonates. Is there a reason why you do that? Because in my experience, I feel like sulfonates are better water soluble than carboxylates, and I'm not sure if that's why you chose either or.
You're absolutely correct. So sulfonate has better water solubilizing properties. It's what is sometimes called a strong polyelectrolyte. So it's fully ionized, and the sulfonate has very, strong hydration. The difficulty was in our early work, we didn't have an easy way to block that as an ester. And so we had to use a direct polymerization. And coming back to the gentleman's question, we didn't know the molecular weight of those polymers early on. And so we started working on the carboxylates because we could make esters with them. And then we could do GPC or other types of analysis and determine molecular weights before we made the polyelectrolytes. So that's kind of where we first got into the carboxyls. But you're right, they're not as strong water solubilizing, but they still work pretty well, the carboxylates, that is. However, it turns out in later sort of work, and this is like within the last 5 years, a postdoc and I together developed a way to protect the sulfonate as an ester. And we make it's a very particular fluorinated ester that you're able to hydrolyze under reasonably mild conditions. And so now we've developed ways that we can make the sulfonated polymers, we can determine the molecular weight, and then we can hydrolyze them to generate the sulfonated polymers. And in addition, the paper that we reported on that, we developed a chain growth polymerization method, so we can make narrow dispersity PPEs. So the PDI is down to like 1.2. That polymerization only got us up to molecular weights around 10,000, but they're very nice polymers. They have really high quantum yields and nice properties.
And sorry, just another question. For your imidazolium pendant polythiophene, you mentioned it's a little bit more cytotoxic than it should be. is it because of the bromine counter-ion, or is it because of the imidazolium itself? Have you compared it to carboxylated B3HD?
So first, if you take the bacteria, you can think of as being positively charged cationic colloids. So, negatively charged, because they have phospholipids. So you need the positively charged polymer to interact with it. If you use a negatively charged polymer, you get no interaction at all. So that's one part. The imidazolium, it turns out imidazole is kind of it's a hydrophobic but cationic group. And so we think it interacts pretty strongly with the phospholipid membrane. So that brings the polymer to the surface pretty effectively. That's one part. But then in addition, the polythiophene we think is really effective at generating reactive oxygen by light irradiation. So it's the combination of the effective binding and the high efficiency of generating reactive oxygen that's characteristic to the thiophene that makes it, at least that's our proposal. I don't have absolute proof of it, but that's what we think is going on.
Thank you.
Mm-hmm.
For the color change of the polymer from the blue to the green in different solvents, so you attributed the change to the aggregated and aggregated structure, right?
Yes.
So I think most likely is a right scenario. However, did you consider the two different excited state in two different solvents, like in methanol, it is local excited state, in water, it's charge transfer state, or maybe different protonated or deprotonated structure?
Yeah, so I think it's pretty likely it's the aggregation. It is a different excited state. It's an excimer-like, meaning that it's aggregated before you excite it, as opposed to coming together in the excited state. But it's a sulfonated polymer, so it's not likely that protonation, because you'd have to go to pretty low pH to change the protonation state of that sulfonate group. So I think our proposal is a good one. Now, it could be that this excimer state has charge transfer character, meaning interchain charge transfer.
Yeah.
And it turns out if you take a donor-acceptor type of polyelectrolyte, so for example, if you've got a benzothiodiazole alternating with some other aryline, when those polymers aggregate in water, they become totally quenched. And so I think in that case, it's charge transfer, but it's interchain. The two come together. I don't know if you understand what I'm saying.
Yes. Thank you. So I think there's a time to close our seminar today, and we thank the speaker one more time.
Thank you.